Hi everybody. Today we are going to discuss, we continue to discuss enzyme kinetics, and today's topic is enzyme inhibition. And the topics that we are going to cover include a reminder of the Michaelis-menten equation, and then we will discuss enzyme inhibition, classification of enzyme inhibitors, competitive, non-competitive, and under non-competitive. We have mixed non-competitive, pure non-competitive, and uncompetitive. Then we'll summarize that, and then we'll discuss very briefly the control of enzyme activity. So the first topic I just want to remind you with the basics of the Michaelis-Menten equation that we discussed in the previous two lectures and we derived in class. So basically, first of all, let's see how an enzyme works. An enzyme has this is a cartoon of an enzyme. It has an active site here. So, you have the substrate comes, it binds to the active site, and then it's split to products, for example, or it forms products, and the next one come in, and so on. So if we have, say, a number of these enzyme molecules, a given number, which is usually much less than the number of molecules of substrate, then there will come a point whereby there is a saturation happening. At the beginning, when the number of substrate molecules is comparable with the number of enzymes molecules available in the medium here, this lower end of this is the substrate concentration versus the speed of the reaction or the velocity of the reaction. In this region, at very low substrate concentration, you double the substrate concentration, you double the velocity of the reaction, they are proportional. And so it is a first order type of kinetics at that end of the scale of substrate concentration. But given a fixed enzyme concentration, if you start to increase the substrate concentration to a very high level, then we'll reach a point whereby you will have a far more molecules of substrate compared to the available molecules of enzyme, and therefore you will eventually hit a saturation point here and a plateau where doubling or tripling or quadrupling the substrate concentration will no longer affect the speed of the reaction, just like the example that I like to say in class. You have a bridge and you have a certain number of toll stations, and suppose that you have a 10 toll station, and if I have 100 cars coming, there is 1 car per second per toll station, so we'll have 10 cars per second crossing. If I have 200 cars, 3,000 cars, 10,000 cars, it won't make any difference in the rate of passing of the cars, because you only have 10 gates, so you have reached a plateau at that point. This is the Vmax. And this is completely explained by Michaelis-menten kinetic model, whereby you have a free enzyme that combines with the substrate and to form the enzyme substrate complex with a rate constant, forward rate constant K1, and the enzyme substrate complex can dissociate back to the free enzyme and the substrate with a reverse rate constant K minus 1, or it can proceed forward and produce the products and the free enzyme again with the so-called catalytic K2, the K2 or the catalytic rate constant, and we ignore the very small K reverse 2 here. And I showed you last time how to derive from that model this very important equation, the Michaelis-menten equation, whereby the velocity of the reaction is given in terms of things that can be measured in the laboratory, such as the velocity, the maximum velocity, the substrate concentration, or the Michaelis constant Km. Now, this equation takes care completely and describes the full behavior of this curve, the full shape of this curve, since, for example, at the low concentration end here, you can ignore S in the denominator, and therefore it becomes V0 is equal to Vmax over Km, and these two are constant. And so it's essentially the speed of the reaction, the velocity of the reaction is equal to a constant multiplied by the substrate concentration to the power 1. So it's a first order reaction. You double the substrate concentration, you double the speed of the reaction in this area here. at very high substrate concentration, so in this region, now S is way bigger than Km, and therefore you can ignore Km in the denominator, and S over S is 1, and therefore the V0 just collapses into Vmax, and it becomes a constant, as you can see, and it's a zero-order kinetics in this case. So from here, we can now proceed. This was a reminder with what we've done last time. Now we can proceed to discuss this curve in the presence of an inhibitor. So the next topic is enzyme inhibition. So an inhibitor is a reagent that will slow down an enzyme-catalyzed reaction. There are several types of these inhibitors. So we will first classify these inhibitors. Inhibitors fall into two broad classes. They can be either reversible or irreversible, that are also called inactivator. In this course, we will not discuss very much the irreversible inhibitor or inactivator, but we will be more concerned with the reversible that interact with the enzyme via non-covalent interaction, because these are the most dominant form in the biological context and also in the drug design world. Many drugs are reversible inhibitors of enzymes, and there are a lot of inhibitors in the biochemical environment of the cell. So this is our focus here, reversible inhibitors. So reversible inhibitor falls into themselves two classes, competitive and non-competitive. And the non-competitive, there are three extremes or three kinds of, it's a continuum really, but it could be classified from an intellectual perspective into a mixed non-competitive, pure non-competitive, and uncompetitive. They all have commonalities, but they are extremes of one continuous range of things. So the general kinetic model for reversible inhibition. So we add, so far that part of the model is exactly identical to the Michaelis-menten model of kinetics, except that we add here an inhibitor. The inhibitor can bind to the free enzyme to form an enzyme inhibitor complex. The enzyme inhibitor complex can bind with the substrate to form an enzyme substrate inhibitor complex, which will lead to no reaction. Now, you could also imagine that first the enzyme binds the substrate, forms the enzyme substrate complex, and the enzyme substrate complex itself can bind the inhibitor to form the enzyme substrate inhibitor complex, and that enzyme substrate inhibitor complex will lead to no reaction. So there are two routes for the inhibitor to bind the enzyme. It could either bind the enzyme, the free enzyme first, and then the substrate binds, or the substrate can bind first and then the inhibitor binds. Now, since we have an enzyme inhibitor complex or an enzyme substrate inhibitor complex, we can also define two dissociation constants. Dissociation constant of the enzyme inhibitor complex, it is called Ki, whereby the enzyme and inhibitor complex dissociate back to a free enzyme and inhibitor, or the enzyme substrate complex, the enzyme substrate inhibitor complex can dissociate to form the enzyme substrate complex plus a free inhibitor, and that's called the Ki primed, the dissociation constant of the inhibitor from the enzyme substrate complex. So in case of a competitive inhibitor, the first case that we will discuss, there is an active site, and the inhibitor has a similar structure to the actual substrate, and therefore competes with the substrate for the active site and prevents the substrate from reaching the active site, and this is the way it slows down the conversion of the substrates to products. As you can see in this little cartoon movie, so here's the substrate cannot enter. The substrate is a T-shaped. This is the inhibitor, the green shaped object here. So the inhibitor comes in, blocks the active site so that the substrate cannot be processed. And therefore, of course, this is not happening all the time, but it slows down the conversion to product significantly. So in this case, you can see very well that it is either since they both, the inhibitor and the substrate, compete for the same site on the enzyme, you cannot have this case at all. You cannot have an enzyme substrate inhibitor. They cannot bind. It's either the substrate or the inhibitor. And therefore, that part is irrelevant in this type of inhibition, and you are only dominated by this part of the kinetic model. It's either the enzyme that binds, either the inhibitor that binds the enzyme or the substrate that binds the enzyme. So this is the kinetic model, and this is the competition. The competition is for the enzyme. Substrate and inhibitor competes. If some of the enzyme is used in this route, less of it is available to go this route, and therefore it slows down the production of the products. So in the competitive inhibition, the Ki prime that I deleted here is just 0 because it's not relevant in this case. It's either the substrate that binds the active site or the inhibitor, and therefore there is no Ki prime in competitive mode of inhibition. So in non-competitive inhibition, the inhibitor can attach itself nearby the active site or partly in the active site so that it interferes with the proper attachment of the substrate with its active site, and hence decrease the activity, decrease the efficiency of the operation of the enzyme. And here it is how it works in a cartoon fashion. Again, the presence of this sometimes here interferes with the proper orientation of the substrate in the active site, and therefore every now and then will prevent the substrate from being converted into products, and this is a mode of inhibition of the enzyme that is non-competitive because they don't compete for the same active site. So in general, the most general non-competitive inhibition is the so-called mixed non-competitive. In other words, the mixed non-competitive inhibition, the inhibitor may bind to an enzyme, a free enzyme, and it may bind to an enzyme substrate complex, because you've seen that the inhibitor in the movie doesn't actually block the active site, it's attached near the active site. And therefore, the inhibitor can bind the enzyme substrate complex, and the inhibitor can bind the free enzyme. So both the Ki and the Ki prime are finite in this case. Ki prime is no longer 0, and this is the full kinetic model. So in pure non-competitive, in this case, Ki and Ki prime, the dissociation constant of these complexes, is exactly identical. In other words, the dissociation constant of the enzyme inhibitor complex is equal to the dissociation constant of the enzyme substrate inhibitor complex. In simple English terms, this means the following. It means that the extent by which the inhibitor leaves its site on the enzyme is unaffected by the presence of a substrate. It's indifferent. If there is a substrate on, whether the enzyme is bound to a substrate like here or not bound to a substrate, does not affect the extent by which the inhibitor leaves that enzyme to give free enzyme and inhibitor, or free enzyme substrate complex and inhibitor. They are not interfering with each other, the substrate and inhibitor in this case. So, excuse me, there is a further type of inhibition, which is this one, and this one whereby the inhibitor cannot bind the free enzyme. And if it cannot bind the free enzyme, it only binds the enzyme substrate complex. So that part of the kinetic model is irrelevant in this case. And this is the uncompetitive type because there is no competition at all whatsoever. And basically, the inhibitor only binds the enzyme substrate complex. It cannot bind the free enzyme, and therefore this part has been deleted. So in uncompetitive mode of inhibition, the Ki now is 0, but the Ki prime is finite. And once you form the enzyme substrate inhibitor complex, there is no reaction. So that with that summary, now we move to discuss each mode of these inhibition in some more detail. So let's look at competitive inhibition. As you may recall from the movie, that in competitive mode of inhibition, both the substrate and the inhibitor compete for one and the same active site. That implies that they should have structural and chemical similarity. Otherwise, they would not bind as a lock and key in the same active site. So now we will discuss in detail that mode of inhibition, the competitive inhibition. So it's inhibitor, reversible inhibitor, competitive reversible inhibitor. That's the place in the taxonomy of inhibitors or the classification of inhibitors. So as we have said before, there is no Ki primed here. It's only why? Because the inhibitor and the substrate compete for the same site. They are similar in structure, and therefore they interfere with each other. It's either the inhibitor or the substrate that will occupy the active site on the enzyme, and therefore once the substrate is on the enzyme, you cannot have the inhibitor also bind to that, and therefore this part of the kinetic model is deleted because Ki prime is 0. We can now give a couple of examples of competitive inhibitors. Here, the first example is the case of succinate and malonate. Succinate is converted to fumarate under the kinetic catalysis of succinate dehydrogenase enzyme. The enzyme dehydrogenates these two methylene groups to form a double bond between them in the fumarate. The malonate has large structural similarity to succinate. It has two carboxylic groups, as you can see, but instead of two methylene groups, you have only one in the malonate, and therefore you cannot form a double bond like the succinate, and therefore there will be no reaction if malonate is bound to the receptor of this, to the active site of this enzyme, SDH. However, it is so structurally similar to succinate that it will competitively inhibit it by often by competing with it to the active site. Second example is that of adenosine deaminase enzyme that catalyzes the conversion of adenosine to inosine via an intermediate that is non-planar due to that carbon here. And therefore, some very similar structures, such as the 1,6-dihydroinosine, which is shown below here, which has a very similar structure to the transition state, can bind competitively into the same active site, the binding site of the enzyme, and therefore it's a competitive inhibitor of that enzyme. So the substrate and the inhibitor have similar structure, and therefore they compete with each other at the same active site, and therefore increasing the substrate concentration favors the binding of the substrate, and increasing the inhibitor concentration favors the binding of the inhibitor. If we write the dissociation constant of the EI, the enzyme inhibitor complex, in terms of the forward and backwards rate constants, then we can write it in this way. We have enzyme concentration can be written as the sum of the enzyme substrate concentration, which is this one, the free enzyme, which is this one, and the enzyme inhibitor concentration, and these are the different three forms of the enzyme in the medium. So that's the total enzyme concentration. The equilibrium constant, or the dissociation constant of the enzyme inhibitor complex, it's a dissociation constant. So you regard this as the reactant, and these are the products. So the dissociation constant of the enzyme inhibitor complex EI, which is K sub I, is equal to the products, which is the free enzyme and the free inhibitor, the concentration of the products over the concentration of the reactant, which is the enzyme inhibitor complex. If you rewrite this in terms, you just switch these two, so the enzyme inhibitor complex concentration is equal to the enzyme concentration stricken into the inhibitor concentration over the Ki. Now if we substitute this equation here, so the enzyme inhibitor concentration, I write it as that, and substitute that here, I get the total enzyme concentration is equal to the enzyme substrate complex concentration plus the free enzyme concentration plus the inhibitor times the enzyme over the dissociation constant of the complex, the enzyme inhibitor complex. So if we take E as a common factor in these two terms, I have E here, so that becomes 1, and that becomes I over Ki, and they are both multiplied by E. So from last time, we know already that the enzyme substrate concentration can be written in terms of the free enzyme concentration times the substrate concentration over the Michaelis constant, which can be rearranged in this way. So I have the E is equal to Km over S times Es. And now, if we substitute this modified equation 8 into the equation number 17 in the previous slide that I repeat here in blue. Blue means we have seen this equation before with that number, so it's just a repeat from last slide. So this is the equation that we derived last slide. And I will just substitute for the enzyme, the free enzyme concentration, the form that I obtained from here. So I plug in Km over SES here instead of E. And in doing that, so this is again from the previous slide, this is the result we obtained. If I multiply now every term by K2, so K2 here, K2 there, K2 here, I obtain that equation. Notice the K2s, K2, K2, because I do know that the total enzyme concentration times K2 is nothing but the Vmax. So I know that this is Vmax. So that converts into Vmax by equation 12. I know that K2 times the enzyme substrate concentration from just the Michaelis-menten kinetic model, it's just V0, so that's V0, so that from equation number 1, that becomes V0, that term, so this becomes V0, that term becomes Vmax, and this is also V0 because it's enzyme substrate concentration times K2, so that becomes V0. So here is my result. Now, that result can be, again, it's repeated here, but I will take V0 as a common factor, so I will pull this out. So I will have a 1 plus that. So I have a 1 plus this times that, which can be rearranged in terms of V0 now. So I get V0 is equal to Vmax over this. So in other words, times 1 over that. So V0 is equal to Vmax times 1 over this squared term. So if I want to simplify this further, I can divide 1 by S, but I multiply, so it's S by S plus this, and I take S as a common denominator, which gets up to get this equation. Now notice this equation is very similar to the Michaelis-menten equation that we derived previously, except that it has a term here. In fact, that part of the equation is just identical. It is the Michaelis-menten uninhibited equation, just as it is. But notice that the Michaelis constant here is stricken by a term in brackets of 1 plus the inhibitor concentration over the dissociation constant of the inhibitor enzyme complex. Now that term, can that term, for example, be less than 1? This is a question. The answer is no. How can it be? These are positive terms. The inhibitor concentration is a positive term. Ki is a positive term. This is more than 0, and therefore this is greater than 0, and therefore this has to be greater than 1. And therefore, as if Km appears to be bigger because of the presence of the inhibitor. The more inhibitor I have, the more Km appears bigger. If you didn't know you have an inhibitor and measure the Michaelis constant as we did last time, you will find that the Michaelis constant is actually larger than if the inhibitor was not present. That factor we call alpha, and it is suggestive to describe alpha times Km as K Michaelis constant apparent, because it can appear as if it is a larger Michaelis constant. It appears as if the enzyme and the substrate have less affinity to one another, which is the result of the presence of the inhibitor. So this alpha factor increases the denominator because, here, this is bigger than 1. So that's bigger than the regular. K apparent is bigger than Km, and therefore the denominator goes up. And therefore, when you divide something by something bigger, the effect on the velocity of the reaction is that it slows down the reaction. So if now we want to plot the Lineweaver-Burke plot for the competitive inhibitor, we have to take the reciprocal 1 over V0 and we invert this on its head. So now I have whatever is in the denominator here comes up. So I have S plus alpha Km, the Km apparent here together, over Vmax and S down. If I divide each term in the numerator of the previous equation by the denominator, I get S over Vmax S plus alpha Km over Vmax S. So I can cancel the S from the first term. It will become 1 over Vmax, and alpha Km over Vmax, 1 over S. Now remember that alpha is nothing more than the 1 plus the inhibitor concentration over the dissociation constant of the enzyme inhibitor complex. This is alpha. I write alpha explicitly here, and then I put in boxes to show you the structure of this equation, this linear equation. It's an equation of a line whereby this is your y, this is the intercept a, this is the x-axis, or the variable x, and this is the slope of the line, and it's an equation of a line. So to now find the x-intercept, you collapse y to 0, because this is where the line will intersect the x-axis. So you put by your own hand the y 0, and you notice immediately that there is a common factor here that you can take out, the Vmax, and you're left with that. With some rearrangement, you can show, in two lines that the x-intercept is nothing but minus 1 over the apparent Km. So it's the negative of the reciprocal of the apparent Km. In other words, it's the reciprocal minus the reciprocal of Km stricken into alpha, or Km stricken into 1 plus the inhibitor concentration over the enzyme inhibitor complex constant, dissociation constant. So the Lineweaver-Burke plot with a competitive inhibitor, when there is no inhibitor, you get back the regular plot of an enzyme with a substrate, because here you have 0, inhibitor concentration is 0 if it doesn't exist, 0 over something is 0, 1 plus 0 is 1, 1 times Km is Km, so it's minus 1 over Km, just like the case that you would expect without even considering the inhibition here. You get it back, so it's the correct limit of the equation. Now, if I start to have inhibitor concentration, suppose I have inhibitor concentration of I, so the apparent Km is bigger here because that term becomes bigger than 1. So you're dividing by something bigger than Km. In other words, its magnitude is smaller, so it shifts back closer to the 0 point here. So the green axis, the green axis comes closer to the 0. And if I double, I increase even more the alpha here, the K apparent the Km apparent is even bigger, and you're dividing by something bigger, so the magnitude is even smaller. So the more the inhibitor concentration increases, the closer the intercept comes to the 0 point. That's a characteristic of a competitive inhibitor, and notice that the Vmax is unchanged. 1 over Vmax is not changed, and therefore, this is a typical curve that characterize or diagnose a case of a competitive inhibitor. If you increase the inhibitor concentration, the x-intercept's magnitude decreases, and the Vmax is unaffected by the presence of the inhibitor. It has the same y-intercept. So this is a simple numerical example from the textbook. Here you have an enzyme that has a Michaelis constant of 8 micromolar micromoles per liter in the absence of a competitive inhibitor. And when you add an inhibitor, the apparent Michaelis constant is 12 micromolar per liter in the presence of 3 micromole per liter of the inhibitor. Now it asks you to calculate Ki. Well, here, first of all, I can calculate the alpha because I do have Km and I do have Km apparent, and the ratio is nothing but alpha. So alpha is defined as the ratio of the apparent Michaelis constant over the Michaelis constant without any inhibitor, the real Michaelis constant. So the alpha is 12 over 8 with the appropriate unit. There is no need for unit conversion here because it's the same unit, so that will cancel, and you get a dimensionless ratio of 1.5 as your alpha. So, and you know that alpha is defined as 1 plus the inhibitor concentration over the dissociation constant of the enzyme inhibitor complex. And I do know the inhibitor concentration. It is given in the question here in the presence of 3 micromole per liter of inhibitor. So I do know that I bracket, I know it. I know the alpha. The only unknown is Ki. Solve for Ki, you get Ki is 6 micromole per liter. Notice that Ki has the dimensions of concentration as it should, since it is a dissociation constant of an enzyme inhibitor complex. And you can work out your units. You have I multiplied by E over Ki. So I has units of concentration, E has units of concentration, so it's concentration square divided by EI, which has units of concentration, so it's the Ki itself has units of concentration. And you can also argue that alpha is dimensionless, 1 is dimensionless, so that term has to be dimensionless. It cannot have any dimensions, so that has to have dimension of concentration to cancel that one. So Ki has the dimensions of concentration, and since I is given in micromolar per liter, micromoles per liter, then Ki is also in micromole per liter. Now, how can you measure Ki experimentally in case of a competitive inhibitor? Well, you obtain two Lineweaver-Burke plots in the presence of a known concentration of inhibitor and in the absence of inhibitor. In the absence of inhibitor, you just, from the Lineweaver-Burke plot, you get the Michaelis constant from the intercept. And in the presence of the inhibitor, just like the previous example, the numerical example has shown, you get -1 over the apparent Km, and from the ratio of the apparent Km to the Km and the known concentration of inhibitor that you put by your own hand, you can get the Ki. That's the basic idea. So to do that, you need a plot without the inhibitor, the blue plot, and one plot with a known concentration of inhibitor, say the green line here, and you get the apparent -1 over the apparent Km in one side from the intercept here, and -1 over Km in the other. And the x-intercept in the case with inhibitor, as you know, is -1 over the apparent Km. So that's the x-intercept, you know it because you can read it from the plot. The Km, you know it because you have got it from the plot of the blue line, the one without the inhibitor. The inhibitor concentration, you know it because you have put it with your own hands. So the only unknown is Ki. So solve for Ki, And I do it here in detailed steps. So at the end, when you solve for Ki, you obtain that the uh, dissociation constant of the enzyme inhibitor complex is minus the x-intercept multiplied by the Km multiplied by the inhibitor concentration over 1 plus the x-intercept times Km, where the x-intercept is the intercept with the inhibitor. And now we move to the next class of enzyme inhibitors, the non-competitive inhibitors. Non-competitive inhibition involves inhibitor binding to both the free enzyme and the enzyme substrate complex. They do not compete anymore for the same active site on the enzyme. So a non-competitive inhibitors binds to the enzyme sites that do not compete directly with the substrate for binding to the active site, which is in contrast with competitive inhibitors, where both bind to the same active site. So it's either one or the other, but here it can be both. It can be one of them, and it can be neither. Where are we in the taxonomy of inhibitor? We are under inhibitors, reversible inhibitors, and we have left the competitive. We are now into the non-competitive inhibitors, and we will define it even better now. So we have three extremes of this. We have the so-called mixed, pure, and uncompetitive. So we'll start with the mixed non-competitive inhibitor type. So we're here in the taxonomy. So non-competitive, under which the mixed non-competitive type. We'll start with that. So the kinetic model for the mixed non-competitive implies that the inhibitor can bind either this free enzyme, or it can bind to the enzyme that has already the substrate complexed with it. So and it does that with different efficiency. So if the free enzyme, the inhibitor can complex the free enzyme with one dissociation constant, and it can bind the enzyme substrate complex with a different dissociation constant. So Ki and Ki prime are not equal, because the extent of dissociation of the inhibitor from the enzyme differs from the extent of dissociation of the inhibitor from the enzyme substrate complex. So, and of course, the ESI will lead to no reaction as usual. So the basic key point here is that in the mixed non-competitive, Ki is not equal to Ki prime. So Ki is the dissociation constant of the enzyme inhibitor complex, and therefore your reactant is EI, and the products are the free enzyme and I, so E times I over EI, while the Ki primed, your reactant is the enzyme substrate inhibitor triple complex that dissociate into enzyme substrate complex and free inhibitor. So it's Ki prime, and these are not equal in the mixed model. So let's remember the equation that we have derived previously for the competitive inhibitors. Competitive inhibitors, you had an alpha stricken into the Michaelis constant here, which was defined as 1 plus I over Ki. But I am not going to derive the similar result in case of mixed non-competitive, but we give you the final result, and the final result here will have this form whereby you have the velocity of the enzyme catalyzed reaction is equal to the Vmax multiplied by the substrate concentration over the apparent Km and the substrate concentration multiplied by another alpha. We will call it alpha prime because the Ki here is prime. So it's called the apparent substrate concentration, if you like. So contrast this with the case of the competitive. The competitive didn't have an alpha prime here. In the case of mixed non-competitive, you have an alpha prime stricken into the substrate concentration in the denominator. So if you reverse, so this is the equation that we've seen last slide, and just we call this term in bracket alpha, and we call this term in bracket with the ki prime alpha prime, and alpha prime are not equal because ki in this case is not equal to ki prime, as I discussed at the beginning. So we have to keep the distinction with the prime. Now, if you take the double reciprocal, if you take the reciprocal of this equation to form the Lineweaver-Burke, to form the basis for a Lineweaver-Burke plot, so we take the reciprocal of 1 over V0 is equal to these terms. The denominator here becomes the numerator over Vmax and S. And if you divide term by term, so alpha Km over Vmax S and alpha prime S over Vmax S, this is what you get with some rearrangement and with explicitly writing the alpha and the alpha prime. So I have 1 over Vmax, 1 over V0 is equal to Km over Vmax times the alpha times 1 over S plus 1 over Vmax multiplied by the alpha prime. So it's equal to alpha, which is this one, multiplied by Km over Vmax times 1 over S plus alpha prime, which is this term, over Vmax. So here, as I often do, the blue equation comes from the previous slide, and I want to show you that when Ki prime is very, very large compared to the concentration of inhibitor, the equation will reverse back to the competitive inhibition case as it should. And by this I mean the following. If Ki prime is very large, what is Ki prime? Ki prime is a dissociation constant of the enzyme substrate inhibitor complex. If it is very large, it means that the numerator is far greater than the denominator. It means at equilibrium, at the given temperature and conditions, at equilibrium, the dissociation products, the enzyme substrate concentration and inhibitor concentrations are far, far bigger than the enzyme substrate inhibitor concentration. In fact, at the limit, the enzyme substrate inhibitor concentration, the tri-complex here, does not form, in fact, when Ki is enormous. So if Ki is huge, you're dividing something here by something huge because it doesn't form, so you get almost, at the limit, that becomes infinity. If that doesn't form at all, the limit would be infinity. Anything divided by infinity is 0. 1 plus 0 is 1. So you revert back to S here, as you can see in this equation. So, I divided by a very large number is negligible. And so you revert back to Vmax S over apparent Km plus S. That's competitive. So in a sense, and if you like Venn diagrams, the mixed non-competitive, which is given by this equation, is the most general form of inhibition that englobes other types, such as at an extreme case whereby Ki prime goes to infinity, that collapses back to a special case, which is the competitive inhibition mode. So the competitive inhibition is the inner circle, is a special case of a more general kinetic model, which is the mixed non-competitive inhibition. Now, if Ki is, in mixed non-competitive inhibition, Ki is not equal to Ki prime. So we have to keep the distinction here between the primed and the non-primed, the alpha prime, which is this one, and the alpha without a prime, because the Ki is not equal to Ki prime. So the distinction has to remain. And again, this implies the following. It implies the dissociation constant of the inhibitor from the enzyme inhibitor complex is not equal to the dissociation constant of the inhibitor from the enzyme inhibitor substrate complex. Now, if we form the reciprocal of this equation, so I take the reciprocal of that side and the reciprocal of that side, the reciprocal of that side is just 1 over V0. The reciprocal of that side, you take every term and divide it by Vmax over S. So that term divided by that, and that term divided by that, and you get these two terms. And in order to form in order to find the x-intercept, well, I place the y by my own hand as 0, and then I find that Vmax is a common factor in the two terms here, so that cancels. And um, by some manipulations, you can show that the intercept in this case will equal to -1 over km multiplied by the ratio of alpha prime over alpha. So now let's consider four extreme cases. The first case is when the inhibitor concentration is 0, and see if you collapse to the right expected result. So if the inhibitor concentration is 0, that is 0. 0 over something is 0. This is 1. Here is the same, and therefore this is 1 over 1. This won't appear, and your intercept is minus the reciprocal of the Michaelis constant, as you would expect without inhibitor. So at least you have that comfort that you recover a known case when you substitute I equals to 0. Now, what if Ki is equal to Ki prime? Again, in English, in words, it means that the dissociation of the inhibitor is independent of whether or not the enzyme is already complexed or not to the substrate. So the enzyme inhibitor complex alone has a dissociation constant of Ki, and the enzyme substrate inhibitor complex has the same Ki, which is given the symbol Ki prime, but numerically they are equal, because in this case, the dissociation of the inhibitor is unaffected by the presence or absence of the substrate. So in this case, you can give one and the same symbol, since these are equal, and since Ki prime and Ki are equal now, so that cancel that here, and the intercept in this case is just -1 over Km, which is the pure non-competitive inhibition model. Now the Ki or Ki prime, they indicate the affinity of the inhibitor to the enzyme or the enzyme substrate complex. So the higher the Ki means the lower the affinity is. In other words, the complex dissociate more readily at equilibrium. So in this first case, if Ki is lower than Ki prime, it means that the inhibitor has a higher affinity to the free enzyme than its affinity to the enzyme substrate complex. In this case, the denominator of this box here, that alpha, will be greater than the numerator, and in this case, that ratio will be smaller than 1. Hence, the plot if this is the plot without the inhibitor, this is just the uninhibited, the normal Lineweaver-Burke uninhibited plot. If this is smaller than 1, and therefore in the presence of the inhibitor, you will find that the intercept, the x-intercept, will be a smaller a number with a smaller magnitude, so the curve will shift this way. So these two things here. First, that the two curves meet at that point, which is in the second quadrant, and also besides the fact that the Km apparent is shifted closer to the 0, the Vmax is higher in the case of the inhibitor. So there are two things that are happening here that are characteristic of this situation. Now let's see the other case. Now what if Ki is bigger than the Ki prime? In this case, it means that the inhibitor has a higher affinity to the enzyme when the substrate is already there than its affinity in the absence of the substrate. So in this case, the denominator is smaller than the numerator, and the ratio now is bigger than 1. And since the ratio is bigger than 1, the intercept will have a bigger magnitude. In other words, it will be further away from 0. So if this is the curve without inhibitor, then the curve with the inhibitor will be shifted away from the 0. So the intercept will be here. This is the Km apparent in this case. And notice also that in this case, the Vmax is also, the reciprocal Vmax is bigger, so it's a smaller Vmax, in fact. And the curves do not meet in anywhere here, but they meet in the third quadrant down there. So this is a characteristic of this situation. So now we come to the pure non-competitive inhibition model. So now we discuss pure non-competitive inhibition, under non-competitive, under reversible, under inhibitor. So the pure non-competitive, in this case, Ki and Ki prime are equal. So there is no need anymore for a prime here, because now the dissociation of the inhibitor from either its complex with the enzyme alone, or its complex with the enzyme when the substrate is already there, are equal. So the inhibitor's dissociation is totally indifferent of the presence or absence of the substrate already bound in the enzyme. And therefore, this Ki and Ki prime are equal. There is no prime in here because they are equal. So this is the pure non-competitive, it is called. It's an extreme case. It's rare. And this is the kinetic model. So in this case, we revert back to equation 19 here, the most general equation. You can see here the prime and the non-prime to distinguish the alpha and alpha prime, but in the case of pure non-competitive inhibition, Ki and Ki prime are equal, in fact, and therefore the distinction is not warranted anymore. So I drop the prime here. These two are equal, and now you can simplify things even further. So now if you take the reciprocal of this to get the Lineweaver-Burke plot, so reciprocal of that side, the reciprocal of this, so that term over that, and that term over that, you get this. So you can simplify it further because now the alpha is the same. It's not even, this is not alpha prime anymore. It's the same alpha, and therefore I can take it as a common factor here. So in fact, the velocity of the reaction is equal to 1 over that alpha multiplied by Vmax S over Km S. And you may recall that this is exactly the Michaelis-menten equation, except that is now divided by 1 over alpha. So there is an effect on the velocity of the reaction in this way. So if I now take the reciprocal of this, so here is the double reciprocal linearized equation. It could be written as 1 over V is equal to alpha multiplied by Km over Vmax times 1 over the substrate concentration plus 1 over Vmax. So this is, again, the equation of the line. Let's see its component. This is the y-axis. That box represents the intercept. So the intercept, the y-intercept is not anymore 1 over Vmax, but 1 over Vmax multiplied by alpha. And then here I have the slope, which is Km over Vmax times alpha, multiplied by the x, which is the reciprocal concentration. So in order to find the x-intercept, you place by your own hand the y as 0, and you will find that you can cancel a few things. The alpha is gone because it's the same in the two sides. You couldn't do that in the other model because alpha and alpha prime were not equal, but here you can. So you can cancel this bracket with that bracket and the 0. You can take away the Vmax, and you're left with 1 here, and with Km over S on the other side. And if you rearrange the intercept, the x-intercept is nothing but minus 1 over Km again, just like as if there were no inhibitor in the case. So you just recover, in this case, the Michaelis constant directly by reading it from the plot. However, notice that the y-intercept, this one, is multiplied by alpha. It's 1 over Vmax multiplied by alpha. So the more inhibitor you have, the bigger the alpha and the bigger the y-intercept. So that's a characteristic of this kind of pure non-competitive inhibition. They both meet here, and they meet exactly on the x-axis at the same position of no inhibitor, the same position of the reciprocal Michaelis constant minus reciprocal of the Michaelis constant. The slope is given by alpha times Km over Vmax, and the intercept here, the y-intercept, is alpha times 1 over Vmax. So it depends, the intercept here depends on the inhibitor concentration. The more inhibitor I have, the bigger the intercept here. So if I double the inhibitor, that curve would be higher and higher and higher in terms of slope and intercept here. So remember, in the case of mixed non-competitive, these two lines would join one time in the second quadrant, one time in the third quadrant, and the case where Ki is equal to Ki prime, which is the pure non-competitive, of course, falls in between the two quadrants. In other words, exactly on the x-axis as it should here, and so that's the case of the pure non-competitive inhibition. So now we come to the last type of non-competitive inhibition, and this is the uncompetitive inhibition. Falls on the taxonomical chart here under non-competitive reversible inhibitors. So this is the general model. In uncompetitive inhibition, the Ki is 0, so that part disappears. And that means what? It means that the enzyme, the inhibitor, has no affinity whatsoever to the free enzyme. So it can only bind the enzyme if that enzyme had already the substrate bound in it. Otherwise, there is nothing's going to happen. The inhibitor is not interested in the free enzyme. Only the enzyme substrate complex can bind the inhibitor, and in this case leads to no reaction. So that's a different kind of inhibition. So here is the kinetic model of that type of inhibition. The inhibitor can only bind the enzyme substrate complex, but not the free enzyme. In other words, the Ki is 0, but the Ki prime is finite and has a value. This is distinguished from the non-competitive inhibition, where I can bind to either E or Es. The result of this, without showing the derivation, is that the velocity, the initial velocity of the reaction, will equal to Vmax times S over the Michaelis constant times the alpha prime stricken into S. So that's the difference from the normal Michaelis-menten kinetics. That alpha prime that multiplies the substrate concentration in the denominator, where alpha prime is 1 plus the inhibitor concentration over the dissociation constant of the enzyme substrate inhibitor complex into enzyme substrate plus inhibitor. So if you take the double reciprocal, if you form the double reciprocal linearized equation, so it's 1 over V0 is equal to Michaelis constant over Vmax multiplied by the reciprocal concentration of the substrate plus alpha prime over Vmax. So let's now connect the plot that you will get as a Lineweaver-Burk plot with the equation, the linearized equation here. So we have the y-intercept, this one, is alpha prime over Vmax, so it depends on the concentration of the inhibitor, obviously. The higher the inhibitor concentration, the higher this y-intercept, and therefore, without inhibitor, if this is the green light with the green line without inhibitor, the more, no inhibitor is alpha prime is equal to 1. Then with more inhibitor, the intercept on the y-axis here increases with alpha prime. On the other hand, if you work out the intercept of the x-axis, then you will find it's minus alpha prime over Km. Notice that it's very similar to the uninhibited one. It's 1 over Km, but here is minus alpha prime over Km. And therefore, it also depends on inhibitor concentration. The higher the inhibitor concentration, the further away from 0 it will become. By the same ratio, since the slope is independent of alpha prime, there is no alpha prime in the slope here. The slope is just Km over Vmax, so it doesn't depend on the inhibitor. So you see all the lines are parallel, but they cut the y and the x-axis at further and further away from zero in both directions, the more inhibitor you have. And this is a characteristic of an uncompetitive inhibitor kinetic model. So let's now summarize what has been said so far about enzyme inhibition. So this is a table from the textbook to which I added one element here, whereby we have the type of inhibition named, the Michaelis-menten type equation with or without inhibitor, and the reciprocal Line-Weaver-Burke equation, which is the double reciprocal version of the Michaelis-menten equation, and the effect of the inhibitor. If I have no inhibitor, you have the Michaelis-menten equation as it is. The double reciprocal version of it is written there, as you know. Effect of inhibitor is irrelevant here because it's not even mentioned. In the competitive type of inhibition, this is the equation, similar to the Michaelis-menten, but you have an apparent Michaelis constant here, alpha Km, and if you take the double reciprocal of this equation and you look at the plot, you will find that the inhibitor increases the apparent Michaelis constant. However, it does not affect the maximum velocity of the reaction, since the intercept in the Line-Weaver-Burke plot is the same for with or without inhibitor. In the case of let's leave this up for a while. Let's go competitive, mixed non-competitive, pure non-competitive, and then we'll go to the uncompetitive. So the mixed non-competitive, the mixed, you cannot drop the prime because the alpha and alpha prime are different. The because the ki and the ki prime are different. In other words, the binding of the inhibitor depends on the presence or absence of the substrate already in the enzyme, and therefore this is the equation, and this is the double reciprocal version of it, and the net effect, the diagnostic of a mixed non-competitive type of inhibition is that the inhibitor decreases the the maximum velocity, the apparent maximum velocity is decreased by the inhibitor, but in its effect on the apparent Michaelis constant is either or. It can increase or decrease depending whether Ki is bigger or smaller than Ki prime. So that's the mixed non-competitive. The pure non-competitive, we can drop the distinction between the alpha and the alpha prime, and therefore you can collect them as 1 over alpha here in front of that term, and the double reciprocal plot will show that in this case the inhibitor does not change the Km, so the Km apparent is the same as Km. In fact, Km is unaffected by the inhibitor. In the mixed type, it can either increase or decrease. Remember, the curve can meet in the first quadrant or the third quadrant, but here they meet exactly on the x-axis, and therefore, in this case, the Km apparent is equal to the Km. There is no effect on the Km. However, the apparent velocity decreases because the intercept of the reciprocal Vmax increases. So it decreases the Vmax apparent. The last one is the uncompetitive, and this is the case where you have the curves with the uncompetitive inhibitor parallel to the one without inhibitor. And in this case, since the alpha prime, the more I have inhibitor, the more alpha prime goes up. And in this case, both curves, both axes, the intercept on both axes increases. In other words, it decreases both the apparent Michaelis constant and the apparent maximum velocity, both decreases. So if you find a decrease in these two, it means that you have an uncompetitive inhibitor, and for the very good reason that the slope, which is Km over Vmax, does not have alpha prime in it. and therefore all the lines are parallel in this mode of inhibition. So by that, I conclude that section on the types of inhibition, and we close this chapter with a very brief discussion of the control of enzyme activity. So by control of enzyme activity, we mean the following. We mean that organisms have several ways of fine-tuning the rate of chemical reactions by fine-tuning the rate, the availability, and the efficiency of the enzymes that are catalyzing its biochemical reaction. So one way is to control the enzyme availability itself. So by altering the rate of synthesis and the rate of degradation of an enzyme, by cranking up or lowering the production of the expression of the genes, for example, that encode for this enzyme. And also it can, but this is more of a slower type of control of enzyme activity, because it takes some time to express the genes as a messenger RNA, and it is translated in the by the ribosome in the cytoplasm to form the enzyme and so forth. So that's kind of a slower mode of control of enzyme activity. A faster way of controlling of enzyme activity is through structural alterations that influence the enzyme substrate binding affinity or its turnover number. There are, for example, other ways whereby you have the so-called allosteric effectors that can change the efficiency of the catalytic site. It could either crank up the efficiency or crank it down. And also there are feedback mechanisms that are not mentioned in the slides, but there are feedback mechanisms whereby the product of an enzyme could act as either an inhibitor, very often an inhibitor, or an accelerator, an allosteric effector of another enzyme. So by allosteric, I mean, this comes from Greek. It means an effector means a modulator of the activity of the enzyme by binding somewhere very far from, often very far from this active site. So by just binding, the effector can either make the enzyme change its three-dimensional shape so that the catalytic area becomes optimum for activity. That's a positive allosteric effector, or a negative allosteric effector can change the three-dimensional structure of the enzyme so such that the active site is not optimum for receiving the substrate. As an example of an allosteric control is the E. coli aspartate transcarbamylase enzyme, ATCase, which accelerates the production of N-carbamoyl aspartate in this fashion from carbamoyl phosphate and aspartate. So carbamoyl phosphate and aspartate form with ATCase and carbamoyl aspartate, as we've seen. This is a summary of the previous slide. And then several steps. There are 6 different enzymatic steps between that intermediate and the product cytidine triphosphate, CTP. And notice that CTP, cytidine triphosphate, is itself an inhibitor, an allosteric inhibitor of ATCase. And therefore, if you overproduce cytidine triphosphate, that product itself tells the enzyme or binds in an allosteric site on the enzyme to make it less efficient to produce more N-carbamoyl aspartate. So it shuts down the production so that it tells the system, shut down my production because there is sufficient of me present. It's a negative feedback. So here, and there are also positive allosteric effectors. ATP, for instance, is a positive allosteric effector. So the presence of ATP will bind allosteric site in an allosteric site at the ATCase enzyme to optimize the shape of the active site so that it's a more efficient enzyme. So there are two cases. There is a case whereby the magenta case here, this is the no effector present. In the presence of CTP, notice the shape of the curve is no longer, this is a typical Michaelis-menten curve and a hyperbolic curve. This one is an sigmoidal, it looks like an S, you know, it has a sigmoidal shape. And this is a typical diagnostic of allosteric effectors, negative allosteric effectors, and this is a sigmoidal shape of a positive allosteric. So if you look at the Km, the Michaelis constant, you take the Vmax, half of it, you go to the curve, you go down. This is the Km, the Michaelis constant of the enzyme substrate pair without any effector, whether positive or negative effector. In the case of a negative effector, like the CTP, which is the product of this chain of enzymatic reaction, which acts as a negative effector, you can see that the Michaelis constant is significantly higher in this case. You go to the curve, you go down, it's a higher Michaelis constant. In other words, the binding of the substrate to the enzyme is far less efficient in this case. However, if you have ATP, the Michaelis constant, the apparent Michaelis constant, becomes lower. In other words, the binding of the substrate to its enzyme is improved by the presence of ATP. So that's a positive effector. This is a negative effector. They modulate it. Notice that this is a hyperbolic curve, the Michaelis-menten kinetics, and these two curves, the red and the green curves, are sigmoidal, which are characteristic of allosteric regulation. In the final count, in eukaryotes, by far the most common modification is the phosphorylation reaction. In other words, the attachment or removal of a phosphate group from a hydroxyl group, for example, from a serine, threonine, or tyrosine residues. So I have the enzyme in an inactive form. Enzyme was, say, serine with an OH. And then there is a protein kinase. And if you remember, kinases are enzymes that catalyze the transfer of phosphate groups. So a phosphate group is transferred from ATP to that OH, free OH, from one of these residues in the active site. And since the ATP triphosphate has lost the phosphate, that becomes adenosine diphosphate. And the third phosphate goes here to make the enzyme, the phosphorylated active site of the enzyme, which is the active form, and to regenerate, you know, to recycle this, you have protein phosphatase that can break down this phosphate and regenerate the inactive form, and is recycled in this manner. And that's the way to control the activity of the active site of an enzyme by covalent modification, which is usually in the form of protein phosphorylations of a side chain of a hydroxyl group of a serine, threonine, or tyrosine residue. Thank you very much for watching, and I'll see you next time.